Okay, welcome back to reliability and survival analysis. Okay, and today we're going to get into distributions. But before that, I'm going to say that risk is not just what it is, what's there. Also, it's about how you feel about it. Last time I kind of give you the hint, the two boyfriend, two girlfriend example, 10 minutes away, 60 minutes, 6 times, 10 minutes, 6 times versus 1 time 60 minutes. It's not the same things. So it's not what it is. Also, it's about how you feel about it. So later on, I will talk about some psychophysics. And when I say psychophysics, some people will argue that's psychology, but I'll say it's mathematical psychology. So the bottom line is, I will talk stuff just like I like some of our students emphasize the Lean Six Sigma stuff. I have no problem with that, as long as you do coding and you prove your argument, which one's better based on numbers. I don't want our graduate or undergrad student out there getting jobs behave like a used car salesman. I prefer you can argue everything's based on algebra, based on calculus, okay? And so from now on, it's all math. And stop me anytime. I'm not a mathematician, so I don't do mathematical proof. But at the same time, I want you to visualize every steps. Try not to memorize it, okay? Some of you have my experimental design before. If you can visualize the stuff, you can get it done quickly. And the only thing that's different from experimental design, if you didn't take it from me, is in experimental design, we only measure distance. How far away from a reference line. But in this class, we'll have some counting process. Means how many times I'm beyond certain limit. How many times, candidate A are 10 minutes late. How many times is within the tolerance of 10 minutes. So we will emphasize a lot this semester. The measurement is based on counting process. It's to count, okay? How hard to count? The devil is in the detail. Next. Risk, okay, is the fully loaded term we're going to use. And there are two functions. From the psychology side is the vulnerability. How vulnerable, okay, for my survival? How vulnerable is this cyber security system? How vulnerable can I get over something, okay? Have you ever taken courses, you basically say, I don't care about my grade as long as I can pass it? Once in a while, right? And I admit, when I was a student, some of the liberal arts courses, I feel like I don't care, as long as I get the credit hours. But so vulnerability, a lot of times, really depends on what you consider is survive, what you consider is good enough. Okay? How can I have a passing grade? But in the physics side, okay, the second function, that is not measuring how you feel. It's really about, hey, how much money do I have? Do I have enough money to pay the rent? Do I have enough money to buy the house? Life, okay? Do you think that the pacemaker I'm going to have is good enough to keep me alive for another 20 years or 30 years? I like to explain this before. For hip replacement, a Titanic's bore socket joints for the trochanter head, for the hip. It's about, including the material and everything, probably $500,000, okay? And the life expectancy for wear and tear of that ball socket joint is probably over 30 years, okay? Do you want to put that ball socket joints in a grandma, 90 years old's hip? But would you like to put that in a teenager, only 18 or 16, with a long life expectancy? So, how long is what we argue. So time and space are the stuff we're going to measure, but again, depends on how you look at it. So combine the two things together. A lot of time we try to minimize vulnerability. It's really about susceptibility. It's about how you look at the threat and then the accessibility. Okay, and now when we combine everything together, we basically said that okay, there is a set of observation, and then we turn that set of observation into historical record. I look at the record and try to decide things. As such, we basically said, if I give you a set of numbers, can you turn them into a distribution or a set of histogram? Why? Because that summarizes that set of data. Okay, and the things I'm going to talk about is that, so if you look at Wikipedia, okay, oh, by the way, I like to use Wikipedia a lot because it's free. And the other thing is that a lot of time the reference they use are good books to start with. And my syllabus probably give you a lot of good books if you want to go deep into it. Okay, but from now on, Tuesdays, you give me a one-page summary of your over the weekend homework. On Thursday, I probably will ask Victoria help me identify a few terms for you to find the definitions, either through Wikipedia, and that way I can force you to read beyond the Excel or SAS exercise I give you, okay? And what is probability distributions? Youngmin, what's your undergrad major? Did you take statistics in undergrad? Oh, okay. So anybody want to define a distribution for me? What is a probability distribution? Okay, so to me, a distribution is a mountain, okay? And the total area under the mountain in the range you cover is equal to 1. So if the total area cover is equal to 1, so you can turn this probability density function into a cumulative density function. So PDF is a mountain, is a hump of pizza dough. And CDF is a transfer function from 0 to 1, okay? And mathematically, there are three things defined by Kolmogorov, the Russian statisticians, called Kolmogorov axiom. Axiom 1, a bunch of events. If X belong to those event set, how many times I go to eat at restaurant 1, how many times I eat at restaurant 2, as long as those restaurants are in the investigation set, E, then I can say that, oh, I've been there 20%, been there 30%. So the total number of time is, or the percentage, must be greater than 0, okay? At most, okay, 100%. Minimum, never been there, 0. Second part is, about this 0 to 1 transfer function is that I can have combinations. Okay, so I've been to, restaurant A, restaurant B. If restaurant A, B, C are the three type of restaurant I'm going to investigate, so put all three type of restaurant together, I equal to restaurant 1, restaurant 2, restaurant 3, combined together. That's all the possibility you can investigate. As such, okay, the total sum of the probability will equal to 1. Okay, those are the three axioms. But in this class, I'm going to introduce another way to look at this. Is the second way is not just looking at a distribution vertically. I can also look at a distribution horizontally. Okay, and in machine learning, they call it the entropy approach. And right now, the only things you need to consider is the following. I have a pizza dough. Say, is this, this almost like a sinusoidal things. Okay, so the total area of the pizza dough equal to 1. Okay, as such, if I'm pulling this pizza dough up more and more, that means I increase the kurtosis. And then if I try to stretch, say, on the right side, and say, oh, I do have some outlier. I do have some very, very strange things happen this way. Think about it, okay? The total area equal to 1. If you pull to the top, this distribution must give some area away in order to go up. Agree? Can you guys see that? You have pizza dough. I'm pulling up or pulling sideways. Either way, okay, you have to give something out. Okay? So, in the visualization of this is that sooner or later, okay, we're talking about a distribution. A distribution about what? Everything happen all the time. Okay? Or there are something, happen all the time, but I have a couple outlier that will shock you from time to time. And then what you're going to do. So what does that got to do with my vulnerability, susceptibility? Just imagine this, okay? You're driving a car, okay? A nice car, okay? I don't care, Mercedes, Lamborghini, one of the good car. 4 o'clock in the morning on I-40 or I-85, no traffic. Would you hold the steering wheel very, very tight, or you play with the steering wheel a little bit so your car can probably kind of wiggle within the lanes a little bit, right? So that's your distribution like this, okay? But now, unfortunately, you're a UNCC student. You don't have that kind of money, so you don't have a Lamborghini. What you have is a beat-up Yugo or very, very old pickup trucks. Bad steering, bad brakes, bad everything. So your car is not that good. You will be very, very careful. Now, if you try to be very, very careful, generally speaking, do you think your variation will be tightened, or you will allow yourself to wiggle a little more? You will try to tighten your distribution, right? Your Lean Six Sigma, you don't allow yourself wiggle too much. So you're just tighten your distribution. If you tighten your distribution, you have very narrow, sharp peak. But unfortunately, suddenly there is a 18-wheel pickup, trucks just passed by you, and you got scared, and then you don't want to get hit. What are you going to do? You move to the next lane, immediately react to it, and then drift a lot more than if you're driving a Lamborghini. It basically kind of like, oh, I can tolerate this. You don't vary much. So when you look at a distribution, you're really not looking at a distribution, right? You're looking at a history of certain behavior. And obviously here are two different type of distribution. They represent two different kind of performance we would like to speculate. So when we look at the shape of the distribution, okay, or build a histogram, sometimes we say that we look at things from the likelihood standpoint or from an entropy standpoint. Okay, I'll give you the computational example in a couple minutes, but first let me show you how these things work. Okay. Okay. And let's imagine this. Okay. I have a bunch of observation, and then the observation range is from 0 to 0 to 5, 5 to 10, 10 to 50, and so on. Okay? And then let's just say that here are a bunch of histograms. Use them all together. Okay? But what if, okay? The number of observation, let me just create some random number here in a second. And doesn't really matter, okay, what kind of random number I have. And all I need to do is just pretend, okay, those are the value I'm going to have, okay? And once I have this, I'm going to turn them into, sum them up together. Okay? And then I'm going to let this equal to the observation. Oh. Divided by this guy. F4. Okay. Okay. And let me just times 100 or 1,000 to make it look easy to recognize. Okay, here we go. Here are some observations of, how I drive that car under different conditions. Slow speed to high speed, 30 miles per hour, whatever. First thing first, okay? What happened? Oh, okay. Okay. But I cannot see well. Okay, here. Suppose that, here's the deal, okay? Here, those are your tally, okay? 0, 105, and so on. First thing first, if I said that, oh, I don't allow you to build a histogram based on the true height. I'm just saying that I have 1, 2, 3, 4, 7 sticks. You're going to use those 7 chopsticks to represent your observation. Okay? What are you going to do in a counting process? Would you put the very, very tall sticks on the small number, or you put tall sticks on the big number? Huh? On the big number. So the biggest one is 241. So the biggest stick should be on 241. Okay? And then same thing, the second biggest stick should be on 157. Huh? Oh, 186? Okay. Just check if you guys pay attention. Okay, the third one will be 157, and so on. Okay? So what is likelihood is suppose, okay, I have a distribution, and I'm trying to use a set of sticks to represent that distribution. So what I'm trying to say here is this. Obviously, oops, what did I do wrong? Maybe, but okay, then I'll cheat. I'll just put this somewhere, one more here, to represent that. So what I'm saying is, if I said that I have that many chopsticks, some long, some short, and I want to use those chopsticks to represent my distribution, my observation, you know that you need to, what? Make the long sticks to match the large observation, short sticks to match the small distribution. So what if, okay? This is the case. Once I have this, what if I said that I have a distribution, insert a shape, okay? I'm going to insert a distribution like this. Control C, Control V. Okay. Here is a mathematical function. Why it looks so ugly, I don't know. But that's the mathematical function I'm going to have. Okay? So here is the question for you. Okay, let me group them together. Arrange. Group. Okay? People, if I want to put the this function to represent those sticks, okay? Would I put this function here, here? Okay, I'll give you three options. Put it here, put it here, or put it here. Where you want to put it? You guys follow me? I'm saying here's a mathematical function, okay? Would you like to locate this total shape on this side or on this side or somewhere in the middle? Here is a mountain to represent the stick figure. You want to put it here, here, or here. A little closer here, would you like that? Why not? Because I don't have a lot of observation here. Why you put it there? It doesn't make sense, right? Put it here, probably okay, but the problem is what? Then I have a bunch of observation. My model said, oh, you will have some observation here, but you really don't have any observation here. So among the three situations, I probably would say I'll match here. I'll put it here. But even this one, is it a perfect fit? No, because I miss some of the observation here. So maximum entropy, maximum likelihood approach. Okay, you guys can read the Wikipedia. To me is what? Try to make taller fit tall area. Short one fit the short area. So basically it said that, hey, let me yank the pizza dough. At what location? When you have a lot of observation area. When you don't have much observation area, don't make that pizza dough rise too high. That's maximum likelihood. Can you guys visualize that now? A bunch of observation. I'm just trying to give me a mathematical function and make that mathematical function tall part as tall as possible to fit it, low part as low as possible. Okay? So this is called maximum likelihood. And later on, we will have a lot of distribution, Weibull gamma to fit that. Okay, especially Weibo. When I work for an insurance company, I love Weibo. The nickname of Weibo distribution is shape distribution. So I can monkey the shape to fit my insurance data really quick. Okay? Everybody with me? Next. Okay. If I don't want to look at the data by looking at the vertical axis, I'm trying to look at the data from the sideway. Okay? When you look at the data from the sideway, you're basically saying your observation in a different way. Okay? So here I'm also have a bunch of sticks. But this time I'm looking at the sticks horizontally. Okay? And in calculus, right? You have a Riemann integral, this vertical integral, and you have Lebesgue integral, the sideway integral. And at the end of the semester, I'll teach another integral called Chauquet integral. It's kind of like half sideway, half vertical. Okay? But here, among all the sticks I can use, okay? Among all the sticks I can use, let's take them away. Okay? And I said that, I have few observation here and few observation here. So I need to find a sticks to basically here. This I'm going to ask you, you want to buy a car from me? Okay? And I would like to know is, okay, what kind of car you can afford? Okay? And if you tell me I can afford a used car for $8,000, that means what? There's no negotiation space, there's no uncertainty. Find me an $8,000 car. Agree? But if I said that, somewhere around 4,000 to 24,000, do you like that kind of answer? If you're the car salesman, you go to a car lot and you encounter a customer. If the customer tells you that, I would like to buy an $8,000 car, you narrow down to the candidate of car really quick, right? But if someone coming in and said that, what kind of price range you would like to have? From $4,000 to, you go to CarMax, you tell them, I want to have $4,000 to 24. That could be a Volvo, used Volvo to a very bad old car, right? That means what? Too much uncertainty. So if I have a long range to cover something, okay, usually I will cover what? A lot of possibility. But what's the problem there? Everything is possible. Then from a reliability, survival analysis standpoint, do you like that kind of answer? Yeah. But on the other hand, if someone just said that, you know what is reasonable, what is tolerable, is right around 25 to 30. I have a very, very tight range. What's the problem as a system engineer? You're talking about something without any possibility to be different. Okay? Victoria, I know it's too early because this is next Thursday's homework, but can you, everybody remember 2 terms I would like you guys to Google next week for next Thursday's homework. One is robustness, one is resilience. Okay? Those 2 terms I would like to use for your Google homework next week. And anybody want to speculate what's the difference between robustness and resilience? If you're a system engineer, you must understand those 2 terms. Graduate student first. Anybody want to speculate? Okay. Okay, so robustness, okay, means insensitive to perturbation, to disruptions, okay? And so a sumo wrestler versus a little kid, okay, who is more robust when someone tried to push him around? The sumo wrestler got a lot of weight and mass and large, right? So robustness usually just means that I'm tough, I'm strong, okay? Resilience, on the other hand, is that I'm susceptible to the perturbation or the disturbance, but I can recover from it. So you kick me, I will move away, but when you when the disturbance stop, I'll back to my original positions. I can recover from it. So resilience, the emphasis is on the recoverability. Robustness means it's just tough and strong. Okay? Now, to handle terrorist attack, okay, you want our system to be robust or you want our system to be resilient? Robust. You cannot handle any surprise. But if you're talking about certain natural disaster, a lot of times you can rebuild, And Katrina in New Orleans, it's about recoverability. How can we bring the livelihood back? Okay, and in this class, a lot of time we're somewhere in between, and we will talk about a lot of reliability issues or survivability issues. Is on one hand we want to estimate how robust we are, basically how likely we can survive without a suscept to the challenge. But then after that, we basically said that, okay, now after something bad happened, how quickly I can recover from it. And the next thing what we're trying to say is that in the maximum likelihood measurement, the vertical, we're just basically trying to hit the big event, the highest probability in the stick diagram. In the entropy world, we basically just said that, let me have the range to cover as much as possible. So the way to think about this is that the entropy approach is about what? Is about cover or shaping the distribution sideways, stretch or compress horizontally. And maximum likelihood is try to manipulate the distribution vertically, okay? But no matter you're doing either way, actually, if you take advanced operations research class, they usually consider they are dual problem. Means that, you guys know dual problem in OR. You probably heard dual problem in OR, right? Yeah, and maximum likelihood and maximum entropy, they also dual problem, okay? And we try to shape the distribution by, let me cover this much. Let me cover certain things that much. Okay, so now I give you the mathematical the concept, vertically and horizontally. So let me now give you a first computational problem. This will be your homework. Okay? So pay attention. No. Okay, thank you. Okay, this one is not working. Let me find a new one. Okay. Consider this. I have two let me just say that I have some event, okay, from 0 to, okay, I date someone 10 times, and there are delay, no delay, or this is the airline, one major airline, 0 on-time performance, 1 minute late, 2 minutes late, or 30 minutes late, just a bunch of late, okay? So first thing first is we need to have a tally, right, or distribution. So right now, if you don't like to look at this probability, just use percentage. 10%, 10%, 10%, 10%, okay? And then I have another airline, airline 2. This is their performance, okay? And this time, let me do this 50. This times 0.9 times 0.7. Okay. And let me sum them up together. This will be more than 1. And then let me redo it. This guy divided by this guy. Okay. And turn them into distribution. And Control C, paste special value. So this is the delay record of, or girlfriend dating, boyfriend dating record, whatever. Okay, it's just some historical data of 2 candidates. Okay, one is equal opportunity, one is this way. Okay, first thing first, which one you like better? The right or the left? You like this one better, airline-wise? But, you know, what's wrong with the first one? Too much uncertainty. Everything is possible. So when we say too much uncertainty, that's why we use the term entropy. Scatter all over the place. Okay? So first thing first is let me calculate the entropy of 2. And to demonstrate that on that side, you got more entropy than this side. Okay? And how to do the computation of the entropy is the following. So you have the probability, and then you take, okay, log 2 base 1 over that probability. Okay. And I would like to use 2 as the base, so I'm going to format cell subscript. Okay, this is the things that you need to calculate. But right now, I'm just help you visualize it first. So this thing's look, okay. Log is a function that curve. Okay. So let me just do this. Log 1 over the probability 2 base. Okay. And we'll do the same thing on this side. Okay. And usually we'll call this information content or uncertainty content. People look at this things, okay? Whatever you call these things, okay, 10%, 10%, 10%, so the value all the same. Agree? But on this side, okay, when you will have a big number with large probability or small probability? Small probability. Okay, so this log 2 things actually was created by Shannon in his information theory. And if you guys later, fortune or unfortunately, take my information class, I'll introduce that. But here, the way how you look at it is what? Things with a lot of small probability usually means that is a big surprise to you. So if I tell you that tomorrow, okay, the sun will come out from the east, will set on the west, is that a big surprise to you? No. So the probability is 1. Log 1 equal to what? 0. There's not much going on there. However, if I tell you that tomorrow, okay, the stock market gonna crash, or the stock market gonna, Tesla stocks gonna jump 3-fold. Okay, how likely that could happen? Not very likely with that kind of big crazy jump. But if that probability, tiny probability actually happened, that will be what? A lot of impact. Would you agree with me? So here, you can consider this value as an impact of something. Okay? So we can call this, the impact factor of certain event. Now, probability, if I'm rather than putting impact, I'm saying impact dollar. Okay? Okay? Here's the impact dollar. Probability times the impact dollar become what? Expected value, right? Right? So we just do the next things is using this terms times the impact. And once you do that, okay, and here we're doing the same thing. Okay? And when we combine this together, the sum of probability times that impact. Here is the total impact, 3.32, 10 times this. And here is 2.7 something. So entropy-wise, the left side got less entropy than the right side. You guys agree with me? You guys agree with me? Huh? My right side, 2.74 is smaller. Okay. And why it's smaller? Because if I ask you to gamble on this, okay, which airline you think that you don't need to prepare, was a lot easy to bet on something? Can you bet on the can you bet on the 10% one? You really don't have to, right? Anything is possible from that event base, the range. But from the right side, think about it. On-time performance is 30.9%. And then 1 minute late is 20. It's easy to figure things out that way. Okay? So first thing first, would you guys agree with me? We can have a measurement based on the uncertainty, based on the entropy. The 2.74 is better because less uncertainty than the 3.32. Everybody agree? Okay, so it's impact times the probability. Yeah.
Just to clarify, so the 2.7 is better?
2.7 because less uncertainty. Okay. And keep that thought for a second, because now I'm going to play a trick with you on this. Okay? Okay, here comes the third airline. You know what's going on the third airline? Okay, let me just do a random number first. Special value. Oh, Control Z. Control C. Pay special value. Yeah, and this just course seek. Okay, let me just do this. Data sort. Column N. Okay. I just, because in class I don't have time to shuffle. I'm just shuffle this number. So look at here. 0 still 30.9, right? But where is 20.6 is at 5. So in other words, if you compare airline 2 and airline 3, the probability value are exactly the same. But the time of the delay is, see here? Where's 20.6? Is over here, right? And 20.6 is over here, right? And where's 15.1? Is way at 9, right? You guys follow me? So in other words, the histogram, I'm trying to assign a value. The second one is from big to small, right? But here, I'm kind of shuffle them around. I'm just randomly plug in a number. And you guys can play this at home. But the thing is that the probabilities, the impact statement is still the same. And when you use the probability times the log impact is still the same. So, oops, something is fishy here. Houston, I have a problem.
You copied the equation from the previous two problems over. It's not collecting the row 0 over airline.
Hold on. 1.6. Huh? No, let me get. Because when I sum them up together, oh, now I see the problem. Okay. Here I solve the problem. Okay, what I'm trying to prove here, look at the uncertainty impact statement, total uncertainty. Victoria, 2.74, still 2.74. So, questions. Obviously, the third airline is not as good as the second airline, right? But from an entropy standpoint, are they the same amount of entropy or not the same amount of entropy? Why? You guys follow me, the questions? Why? So in other words, is that entropy only care about the sticks. You have a long stick, you have a short sticks. Does it matter where the location of the stick? you can shuffle this 10 factorial, right? I don't know, 5,500 different way of sequencing. But no matter which sequence, the entropy is still the same. So maximum entropy approach only care about what? How much can I cover in the total area? It doesn't really, when you do the computation, it doesn't give you the intuitions on the locations. They only care about how scattered this whole things cover a certain range. Okay, that is the difference between the two different concepts. Right now, just keep that in mind, because later on I will show you, certain benefit when to play using maximum likelihood, when to play entropy. But people, I would like to just show you another example. Is that suppose I have a regions or distribution look like this, a 4 or say a 5 by 5 regions, a two-dimensional distribution, x1, x2. So this is here, let me do it. So I will have 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5. Okay, and then let me just do the random number real quick. And Control C, paste special value. So now I can lock the total value. Okay, so if I have a two-dimensional distribution, okay, it's still discrete, but when I sum all the sticks together, is equal to 1. So if I look at the shape of these things, no, this is not what I'm looking for. I'm looking for a stick diagram. What is, huh? Yeah, a two-dimensional histogram. Oh, not this kind. I still want to go to two-dimensional way. That's okay. Let's just use the surface. No. Just go back to surface. Okay.
Like this?
No, no, no. Just as it is. Yeah. Use the second one. Okay, thank you. Okay. Well, what I really want is to show that a 5 by 5 floor, right? And basically on this 5 by 5 floor, every square tile, I have a height. And I know the total height together is still equal to 1. And so can I calculate a two-dimensional histogram and figure out the entropy? Just probability times log 2, 1 over p probability 2 base, right? Now, same things. If I shuffle, so if I calculate entropy there, and I shuffle around the location and say, oh, I don't want the tallest sticks at a full 4. I want to move them to switch was 1, 4. So if I move those 5 by 5, 25 value without changing the value, just shuffle them around, okay, would that change the entropy at all? No. So the bottom line here, the take-home message here is that entropy computation only care about the total number of sticks you can monkey around. Doesn't really care, as long as within that range. As long as you don't change the value, the total amount of uncertainty, the total amount of things you can scatter around remain the same. Okay? Okay. Now, let's back to the lecture now. Huh? We're running out of time? Okay. Huh? 5 more minutes? Oh, 15 more minutes. Okay. So let's do the first parameterized distribution, uniform distribution or your random number distribution. And so if it's from 0 to a, and the height will be 1 over a. Why? Because 1 over a times a equal to 1. So the total area of the pizza dough equal to a square, a rectangle 1. Agree? So if this is 20, this will be height will be what? 1 over 20. If this is 30, the height will be 1 over 30. So people, just intuitively, would you agree with me? The longer the A, the scatterness will spread out even more. Okay, the spread will be more, and the entropy will be more. Agree? Next, okay? I don't care what is your A, so where is the average? The average will be right in the middle. So the average will be A over 2. And then, by definitions, okay, the variance should be the expected value of the mu square minus the 1 over, I'm sorry, will be mu square minus mu 2 prime. And as such, 2 over a squared 3 minus this, you will have the standard the variance is a squared 12. And again, look at the variance, okay? The larger the a, you scatter more, so you have more variation. And then the square root of this is your standard deviation. What if we do uniform distributions, and then we're saying that I don't want you to start from 0 to a. I want you to start from a to b. And then I would like you to evaluate the mean and standard deviation and so on. That is boring. So I find a different problem for you to play with. Okay? And here's the problem. Oop, I only have the scatterness. Let me do it differently. Let me find another sheet. Okay? So here's the distribution I'm interested in. Is, let's say A is start from, give me a number. A start from where? 15. B ended at what? 90? Okay, 15 to 90. Roger that. A equal to 15. And then I have to do it. B equal to, you say 90, right? Okay, and then now we would like to build, so I have a bunch of random number. Okay, the random number, I'll start from here, and I will do it for $10,000 times. Okay. Now, if I have the number Okay, next things, look at this, how to generate that distribution. Equal to A plus P times B minus A. So first I need to have my A term. Okay, so here's my F inverse. Okay, F inverse P. And what F inverse P really means is generate a random number based on that distribution. So this is the random number I'm trying to create. Okay, so equal to A is 15 plus probability, whatever the probability you give me, and monkey around, floating within the range from 90 to 15. Okay, so first thing first is this term need to be locked. This term need to be locked. F4 will help you lock them. Okay, now we generate the random number. 81 looks okay, right? Because 81 is between 15. Okay, so let's just do this. Control C. Control V. Oop. Houston, I have a problem. Go back. Control C. Control V. Okay, so let me lock the value. Pay special. Lock the value. Just do a simple check. Hey, show me your random number. Insert, scatterness. Okay, so far so good, right? Monkey around all the dot is between 15 to 90, right? Next. What if this is not the observation? Okay, let me not get rid of it. Control. What if, okay, I would like to assume this is not from a simulation. This is a bunch of observation from my dating record. I have 10,000 dating record. I would like to know the delay of that 10,000 airline performance, whatever dating record. Is that follow certain distribution I would like to use? So first thing first is make sure data analysis is there. Oh, they don't. So I need to do a data analysis. How to, huh? File, options, add in, and what should I add in? I need to have the solver and, huh? Yeah, I mean, don't talk, just come help me so we can save time. I want to build histogram, so just help me make sure I have the histogram there. Oh, good job. Analysis tool pack and, okay. Yay, okay, thank you. So now, let me just have the bin built first, okay? So my bin will be from 15 to 90. So I'll use every 5 as my bin size, otherwise I'll have too many bin. Okay, I need one more. Okay, so data analysis, histogram. Okay, input range from here to here. Bin range is from here to here. And if you do that, you can tell here is a histogram we just built. Okay, this time is not a random number I built, is a change to chart type. Okay, so look at this. 0 to relatively, they are equal height. Would you agree? So now, if I consider this is the record, what can I do next? I can turn this, okay? Into a percentage. And what will be the percentage? Will be every one of them divided by 10,000, right? Okay. And next, I would like to say if this is a PDF approximation, and let me have a CDF approximation. How to build a CDF approximation? I'll start from nothing. And then every time I'll use what I have before plus my current observation. So if you do that, guess what will be the last number? 1. So if you show this, you will have 3 different plots. The first plot, I should start from here, is my PDF variation. And then if I turn my PDF approximation based on percentage, look like this. And then if I use this to build a CDF, I will have a nice looking from 0 to 1 straight line. I grow. The transfer function, since it's a uniform distribution, is a step function. Every step is equal size. Grow, grow, grow from 0 to 1. Okay, so now Victoria, please help me. Let's form the exercise or homework for today, for this week. I would like you guys, okay, first play with the entropy, okay, and don't copy mine. I would like you to do this. First, create a uniform distributions entropy example, and then create a entropy example that no matter what will be smaller than a uniform distribution. That should happen very easily. But then I want you to challenge yourself and speculate how to do that is, okay, if you have an entropy distribution, let's just say that it's 2.74 right now. I want you to make that 2.74 even smaller. So drop here. Everybody agree with me? My original uniform distributions entropy is 3.32, right? And then I obviously did something, make them 2.74, okay? But I'm not happy with that number. I would like to drop even more. And I would like to see who can make it drop even more. And I can tell you how to drop very, very quickly to 0. Just have one number. But that's cheating. I want you to drop somewhere around 10%. Okay? And that basically make you speculate what the heck is this entropy things. It's basically how to measure and handle uncertainty. And if we want to talk about survival and reliability, we have to know how to measure uncertainty. Agree? So you follow my instruction? Uniform distribution as my baseline. And then drop and find a way to make that entropy drop even more, another 10% more. Okay? That's the entropy problem. Okay? And you can refer, please follow the lecture now, so, or follow the videotape. Okay? The second questions, okay? Create a 6 by 6 distribution. Calculate the entropy. Okay? It's just P times 1 over, okay? And then move the value around. Shuffle those 36 number around and calculate the entropy and prove that entropy is location independent. Because as long as I have those 36 value locked, then no matter how you move them, your total amount of entropy should be exactly the same. Okay? Prove that through the toy problem. And the third one is, okay, create uniform distribution with random number. Create 10,000 sample like what I did, but don't use the range I give you. Use a new range, and at the end, show me 3 charts. The histogram chart or the PDF based on count, based on event count, based on percentage, and then convert the percentage chart into a CDF transfer function from 0 to 1. Okay? That's your homework or take-home exam this week. Everybody agree? Okay.
And that's due when?
Do same thing, Monday midnight.
Monday midnight.
Yeah, and so by Tuesday, I can collect, by Tuesday, please give me something, a 1-page simple summary. What have you learned from those 3 examples? No need to be wordy. Actually, if you can give me a knockout punch, 1 sentence and say, this is what it means, then that'll be the best. Okay?
Wait, can you repeat that second part again?
Just summary of what you learned from those 3, the homework or exam problems. Yeah.
Should we submit the Excel file?
Yeah, I will, just like previous one, I'll create, I need to double check your file, make sure you've done the work yourself, okay? I won't mind you guys discuss, in the DOE, I said the same thing. The only thing I hate is when people copy other people's homework, and it's very easy to figure that out, is when you have the spreadsheet, exact location, use exact symbol, and that bothers me, okay? And try to learn and practice by yourself, okay?
So you use the summary, you want us to turn that in physically, like we did?
No, summary, I want the,
Okay.
on paper, but the exercise, I want to see your Excel, okay? Okay,